You walk every day to the kitchen, to your car, down the street to grab coffee. Walking is the most fundamental thing humans do. We have been doing it for roughly 6 million years. It is so ordinary, so automatic, that you probably do not even think about it. Your great-great-grandparents walked. Their great-great-grandparents, going back through the millennia, through the agricultural revolution and the ice ages and the migration out of Africa, all the way to the first hominid who stood upright on the African savanna. Your ancestors walked. Walking is literally built into you. The curve of your spine, the angle of your pelvis, the length of your legs relative to your arms, the precise architecture of your feet with their 26 bones and over 100 ligaments. All of it evolved for one purpose: to carry you forward, one step at a time. But here is a question that might never have crossed your mind. What if you kept walking? Not around the block, not across a country. What if you walked around an entire world? And not just any world. What if you walked around every world? Mercury, Venus, Mars, the gas giants, the ice giants, every planet in our solar system, one footstep at a time. How long would that take? The answer is stranger than you might expect. It is also more beautiful, because when you start doing the math, when you start measuring planets in footsteps instead of kilometers, something shifts. The solar system stops being an abstraction. It becomes real, viscerally, physically real. So let us take a walk, the longest walk imaginable. Let us put one foot in front of the other and circle every world that orbits our sun. Before we take our first step, we need to establish some ground rules, and we need to understand what we are actually measuring. First, the walking speed. How fast does a human being walk? This is not as simple as it sounds. A 2020 study published in the journal Gait and Posture found that the average preferred walking speed for healthy adults is approximately 1.31 meters per second, which works out to about 4.7 kilometers per hour. The Centers for Disease Control and Prevention cites a range of 2.5 to 4 miles per hour for adult walking, with the average landing around 5 kilometers per hour. That is a comfortable pace most people maintain when they are not in a hurry, but not dawdling either. About 100 steps per minute. For our journey, let us be generous, but realistic. We will use 5 kilometers per hour as our baseline. That is a sustainable pace for long-distance walking, the kind of speed that endurance walkers maintain for hours and days at a time. And we are going to need that endurance because we are not going to stop. Well, technically, we are going to walk 8 hours a day. That seems fair. Even the most dedicated pedestrians need to sleep, eat, and occasionally sit down. 8 hours of walking per day at 5 kilometers per hour gives us 40 kilometers of progress every single day. That is our formula. 40 kilometers per day, every day. No breaks, no holidays, no sick days. Is this realistic? Human beings have accomplished remarkable feats of endurance walking. In 1976, Jesse Costendo walked 228.9 kilometers in 2004 hours. The world record for the farthest distance walked in a single day. George Megan walked 19,019 miles from the tip of South America to the northern coast of Alaska between 1977 and 1983, averaging about 14 kilometers per day over nearly 7 years. Jean Beliveau walked around the world between 2000 and 2011, covering 75,000 kilometers across 64 countries in 11 years. Our 40 kilometers per day is aggressive but not superhuman. It is the pace of a dedicated walker, someone who treats walking as a profession rather than a stroll. It assumes good conditions, proper nutrition, and no significant injuries. Of course, we will be walking on planets that do not have good conditions, proper nutrition, or medical facilities. We will be walking on planets that would kill us in seconds through heat, cold, pressure, radiation, or simple lack of air. But we said we would ignore that. This is a thought experiment, not a mission plan. Now for the measurement. What exactly are we walking around? Planets are not perfect spheres. They bulge at their equators because they spin. Jupiter, which rotates once every 10 hours, bulges dramatically. Its equatorial diameter is nearly 10,000 kilometers wider than its polar diameter. Saturn is even more oblate relative to its size. So when we talk about walking around a planet, we need to specify we are walking around the equator, the longest possible path around each world. This is the equatorial circumference. Why the equator? Partly because it is the longest route, which makes our journey the maximum possible challenge. Partly because equatorial data is what astronomers typically report, but also because the equator has a kind of symbolic resonance. Every planet's equator is the line that divides its northern and southern hemispheres, the great circle around which the world turns. To walk the equator is to trace the fundamental geometry of a world. And one more thing, we are imagining, for the purposes of this thought experiment, that we can actually walk on these planets. We are ignoring, for now, the fact that you cannot walk on a gas giant. We are ignoring the crushing pressure of Venus, the freezing vacuum of Mercury's dark side, the radiation bath around Jupiter. We are simply asking, if you could walk, how long would it take? The physics of gravity, though, we will keep, because gravity changes everything about how humans move, and the gravity on each planet is wildly different. On Earth, gravity accelerates objects toward the center of the planet at 9.8 meters per second squared. This is what we call 1G. It is the gravitational environment in which our bodies evolved, in which our muscles and bones developed, in which our cardiovascular systems learned to pump blood. 1G is quite literally the baseline of human existence. On other planets, gravity can be lighter or heavier. Lower gravity means less effort to walk, but also less traction, less control, more bounce. Higher gravity means every step requires more energy. Every stride becomes more labored, and your entire body feels heavier. Researchers have studied how gravity affects human locomotion using sophisticated simulators and parabolic flight experiments. The results are illuminating. At lower gravity, humans naturally transition from walking to running at slower speeds. The walk-run transition, which occurs at about 2 meters per second on Earth, happens at progressively lower speeds as gravity decreases. On the Moon, with its 0.16 g, astronauts found that running and hopping were often more comfortable than walking. At higher gravity, the opposite happens. Walking becomes preferable to running because running's impact forces become prohibitive. Researchers estimate that humans could theoretically walk at up to about 4 times Earth's gravity with significant training, but it would be exhausting and probably damaging over time. As we visit each planet, we will note its gravity and consider what that means for our hypothetical walker. Let us begin. Our first destination is Mercury, the smallest planet, the closest to the Sun. Mercury has an equatorial diameter of 4,879 kilometers. To find the circumference, we multiply by pi. That gives us approximately 15,329 kilometers around the equator. At 40 kilometers per day, that works out to about 383 days of walking, just over a year to circle the smallest planet in our solar system. That might not sound too bad. People have done comparable walks on Earth. George Megan walked 19,019 miles from the southern tip of South America to the northernmost point of Alaska between 1977 and 1983. That took him nearly 7 years, but he was not walking in a straight line, and he was dealing with terrain, borders, and the logistics of human civilization. Mercury, in our thought experiment, is just walking. Pure, uninterrupted walking. But here is where it gets interesting. Mercury's surface gravity is only 3.7 meters per second squared, compared to Earth's 9.8. That means you would weigh only about 38% of what you weigh on Earth. What does that do to walking? Researchers have studied this extensively, partly because of its implications for future Moon and Mars missions. Studies using NASA's Active Response Gravity Offload System, which simulates reduced gravity, have found that humans adapt their gait significantly in lower gravity environments. Your stride changes, your bounce increases. The Apollo astronauts discovered this firsthand on the Moon, where gravity is even lower than on Mercury, at just 1.6 meters per second squared. On the Moon, the astronauts found that a loping, hopping gait was often more efficient than normal walking. Neil Armstrong noted in his technical debrief that balance while walking was not difficult, but high jumps had a tendency to tip him backwards. Buzz Aldrin observed that the 1 foot in front of the other walk worked better than the kangaroo hop, though both were possible. On Mercury, with gravity slightly higher than the Moon, but still dramatically lower than Earth, you would likely develop a similar bouncing gait. Your steps would be longer. You might cover ground more efficiently once you adapted. Or you might find, as some researchers have suggested, that reduced gravity actually slows you down because you cannot push off as effectively. A 2019 study in the Physics Teacher, examining the effects of different gravity levels on human locomotion, found that humans could theoretically perform normal walking at up to about 4 times Earth's gravity, but optimal efficiency occurs close to Earth normal. In lower gravity, walking becomes less efficient, but running and hopping become more attractive options energetically. For simplicity, let us assume our walking speed remains constant at 5 kilometers per hour. Our 380 3-day Mercury circuit stands, but there is something else about Mercury that would make this walk utterly surreal. Mercury rotates incredibly slowly. 1 Mercurian day, sunrise to sunrise, takes 176 Earth days. And because of Mercury's eccentric orbit and the peculiar relationship between its rotation and revolution, the sun does strange things in Mercury's sky. It rises, pauses, briefly reverses direction, then continues on its way. If you were walking Mercury's equator, you would experience about 2 complete day-night cycles during your year-long journey. 2 sunrises, 2 sunsets. The terminator, that line between day and night, would sweep past you twice, and the temperature swings would be lethal. The sunny side reaches 430 degrees Celsius. The dark side plummets to minus 180 degrees Celsius. Mercury has essentially no atmosphere to distribute heat. But we said we would ignore the deadly aspects. We are just walking 1 year and 18 days to circle Mercury. Our first planet is complete, but consider what this journey would actually look like. Mercury has almost no atmosphere. The sky above you would be black, even during the day. Stars would be visible alongside the Sun, which would appear about 3 times larger than it does from Earth. At perihelion, when Mercury is closest to the Sun, that blazing disk would be even more imposing, almost like a cosmic spotlight tracking your progress across the cratered terrain. The landscape itself would remind you of the Moon. The Caloris Basin, one of the largest impact craters in the solar system, at 1,550 kilometers across, would stretch beyond your horizon if you walked near it. Mercury is old. Its surface has been battered by 4.5 billion years of impacts, and without atmosphere or water to erode them, those ancient scars remain fresh. NASA's MESSENGER spacecraft, which orbited Mercury from 2011 to 2015, revealed a world of extremes. Radar data from MESSENGER even discovered ice at Mercury's poles, hiding in permanently shadowed craters where the Sun never reaches. In those eternal shadows, temperatures can drop to -200 degrees Celsius, while just a few kilometers away, in direct sunlight, the surface bakes at temperatures that would melt tin. Your 383-day walk would take you through this landscape of violent contrasts. You would walk across plains of ancient lava, around the rims of craters named for artists and musicians, past cliffs called lobate scarps that formed as Mercury's core cooled and the whole planet shrank. And you would be profoundly alone. Mercury has no moons, no companions in the sky except the Sun and the stars. Venus comes next, Earth's twisted twin, almost exactly the same size as our home world, but with a surface that would kill you in seconds. Venus has an equatorial diameter of 12,104 kilometers. Its circumference is approximately 32,205 kilometers. At 40 kilometers per day, that is 951 days of walking. 2 years and 7 months. The gravity on Venus is 8.9 meters per second squared, about 90 to 1% of Earth's. This is close enough to normal that your walking gait would feel almost unchanged, a little lighter on your feet perhaps, but recognizably Earth-like in its mechanics. The Venusian environment, however, is anything but Earth-like. Between 1970 and 1982, the Soviet Union landed a series of Venera spacecraft on the surface of Venus. Venera 7, which touched down on December 15, 1970, became the first human-made object to successfully land on another planet and transmit data back to Earth. It measured the surface temperature at approximately 475 degrees Celsius, hot enough to melt lead. The pressure was about 90 atmospheres, equivalent to being 900 meters underwater on Earth. Venera 13, which landed in 1982, survived for 127 minutes before succumbing to the conditions. It transmitted the first color photographs of the Venusian surface, showing a bleak landscape of flat rocks under an orange sky. The atmosphere is thick with carbon dioxide and laced with clouds of sulfuric acid. In our thought experiment, we walk anyway. We would walk through that crushing, superheated, acidic atmosphere for 2 years and 7 months. We would see the same rocks Venera 13 photographed, stretching in every direction. The sun would be a vague brightness through the perpetual overcast, providing enough light to see, but never breaking through the clouds. Venus rotates even more slowly than Mercury, and in the opposite direction from most planets. A single Venusian day, from sunrise to sunrise, takes 117 Earth days. During our 951-day journey, we would experience about 8 complete day-night cycles, 2 years, 7 months, and 8 Venusian sunrises. The most remarkable thing about walking on Venus might be what you would hear. Venera 13, during its 127 minutes on the surface, transmitted the first recording of sounds from another planet. The audio captured the sound of Venusian wind, the whine of the drill collecting samples, and the pop of the lens cap being ejected. The wind on Venus's surface is gentle, only about 0.3 to 1 meter per second, a mild breeze by Earth standards. But because the atmosphere is so dense, that gentle wind would exert significant force on your body. Walking into even a light Venusian breeze would feel like wading through water. The sky above you would be orange, possibly with a slight greenish tint, depending on altitude and cloud conditions. The thick clouds scatter sunlight so thoroughly that there are no shadows on the Venusian surface. Noon and dawn look almost identical in terms of lighting. You would walk in a perpetual overcast glow, like an eternal cloudy afternoon. And despite Venus being closer to the sun than Earth, less light reaches its surface because of those thick clouds. Venera 8 measured the illumination level as similar to a very overcast day on Earth, with visibility of about 1 kilometer. You could see, but not clearly, not far. 2 years and 7 months in that orange twilight, walking through a landscape of volcanic rocks and lava flows under clouds of sulfuric acid, in heat that would cook you instantly, and pressure that would crush you flat. Venus was once thought to be Earth's twin. In the early 20th century, some astronomers speculated that beneath those clouds might lie jungles and swamps, a tropical paradise. Science fiction writers imagined dinosaurs and primitive life forms. The Venera probes shattered those dreams. We skip Earth. You have already walked on Earth. You know what that is like. But consider this. Earth's equatorial circumference is 40,075 kilometers. At 40 kilometers per day, it would take 1,002 days to walk around our own planet. About 2 years and 9 months. This has never been done in a straight line. The oceans get in the way. But various adventurers have circumnavigated the globe on foot, using available land routes and transportation across water. Dave Kunst holds the Guinness World Record for the longest journey on foot, covering approximately 23,300 kilometers between 1970 and 1974. And he traversed 4 continents doing it. The true equatorial circumference is impossible to walk because so much of it is ocean. The Pacific alone covers more than half the equatorial length of the planet. If you tried to walk around Earth at the equator, you would spend most of your time swimming. But consider what it would mean to walk that distance on land. 1,002 days, 2 years and 9 months. You would walk through deserts and jungles and grasslands. You would cross mountain ranges and river valleys. You would experience every climate Earth has to offer, from equatorial heat to high-altitude cold. You would encounter thousands of species of plants and animals, hear dozens of languages, pass through dozens of nations. Earth is the only planet in our solar system where walking is not merely possible, but meaningful, where the terrain varies, where there are things to see and touch and smell, where the act of walking connects you to a living world. Our theoretical Earth circuit takes longer than Kunst's actual journey because we are going the full equatorial distance, not the shortest land route. Keep that Earth number in mind, 1,002 days. It becomes a useful reference point for what comes next. Mars, the red planet, the world that has captured human imagination more than any other. Mars has an equatorial diameter of 6,792 kilometers. Its circumference is approximately 20 to 1,344 kilometers. At 40 kilometers per day, that is 534 days of walking. About a year and a half, smaller than Earth, smaller than Venus, but not as small as Mercury. The gravity on Mars is 3.7 meters per second squared, identical to Mercury's. Once again, you would weigh only 30 to 8% of your Earth weight. Once again, your gait would adapt, becoming bouncier, more like the locomotion the Apollo astronauts developed on the Moon. Studies of locomotion in simulated Martian gravity have found that humans naturally transition from walking to running at lower speeds than they do on Earth. The walk-run transition, which occurs at about 2 meters per second on Earth, happens at lower speeds in reduced gravity. You might find yourself running more than walking, simply because it feels more natural at Martian gravity levels. The Martian day is almost exactly the same length as an Earth day, 24 hours and 37 minutes. This would make our walk feel strangely familiar. The sun would rise and set on a rhythm almost identical to what we know. But the Martian year is nearly twice as long as Earth's, lasting 687 Earth days. During our 534-day journey around Mars, we would experience one complete cycle of Martian seasons. We would walk from summer into autumn, through winter and back into spring, though on Mars those seasons are defined more by dust storms than by temperature variation. Mars has a thin atmosphere, about 1% as thick as Earth's. The temperature swings between day and night are dramatic. Daytime at the equator might reach 20 degrees Celsius in summer, but at night it plummets to minus 73 degrees Celsius or colder. Our 534 days on Mars would be cold, dry, and rust-colored. The iron oxide dust that gives Mars its red appearance would coat everything. Every step would leave a footprint in that fine Martian regolith. A year and a half to circle Mars. We are still in the realm of human endurance. People have walked for longer than that without stopping. The Martian landscape would be hauntingly familiar and utterly alien at the same time. The terrain resembles certain desert regions on Earth, the dry valleys of Antarctica, or the high deserts of Chile, but the colors are wrong. Everything is shaded in rust and ochre and burnt sienna. The sky, instead of blue, is butterscotch during the day, sometimes turning pink or even greenish at sunrise and sunset. Olympus Mons, the largest volcano in the solar system, rises 1.9 kilometers above the surrounding terrain. If your equatorial walk took you near its base, you would barely notice. The mountain is so enormous, with a base 600 kilometers across, that its slope is too gentle to see. You would be walking uphill for days before you realized you were on a mountain at all. Valles Marineris, the Great Canyon system that stretches 4,000 kilometers across the Martian surface, would be a more dramatic encounter. In places, it drops 7 kilometers deep. From the rim, you would see layers of rock exposed by ancient water flows and tectonic activity, a geological history book laid open. The dust devils that roam Mars would be visible from kilometers away, spinning columns of fine particles that can reach 20 kilometers high. The rovers have photographed them repeatedly, and the Ingenuity helicopter has even flown through their wakes. Walking on Mars, you would see them dancing across the terrain, sometimes passing close enough to pelt you with grit. At night, the stars would appear brighter than they do from most places on Earth. Mars's thin atmosphere scatters little light, but the moons, Phobos and Deimos, would draw your attention. Phobos, the larger moon, orbits so close to Mars that it rises in the west and sets in the east, completing an orbit in just 7 hours and 39 minutes. During a single Martian night, you might watch Phobos cross the sky multiple times. It would also appear to move visibly against the stars as you watched, covering its own width in just a few minutes. Phobos is doomed. It is slowly spiraling inward toward Mars approaching by about 2 centimeters per year. In perhaps 50 million years, it will either crash into Mars or break apart into a ring. If humans are still walking on Mars then, they will see a very different sky. Deimos, the smaller and more distant moon, moves more sedately. It rises in the east and sets in the west, like our own moon, but takes about 30 hours to cross the sky. It would appear as a bright star, barely large enough to show a disk to the naked eye. But now we leave the rocky planets behind. Jupiter. This is where things change. Jupiter has an equatorial diameter of 142,984 kilometers. Its circumference is approximately 449,197 kilometers. Let that sink in. Mercury's circumference was about 15,000 kilometers. Earth's is 40,000. Jupiter's is nearly 450,000. At 40 kilometers per day, walking around Jupiter would take 11,230 days. That is 30.7 years. 30 years of walking. An entire generation. You could start walking around Jupiter as a young adult and finish as an elderly person. Children born when you started would be having children of their own by the time you completed your circuit. No human has ever walked for 30 consecutive years. The longest walks in human history have been transcontinental journeys lasting a few years at most. 30 years of daily walking every single day without fail is beyond anything our species has attempted. But the time is not the strangest part. The gravity is. Jupiter's surface gravity, measured at the 1 bar pressure level in its atmosphere, since there is no solid surface, is 24.8 meters per second squared. That is about 2.5 times Earth's gravity. On Jupiter, you would weigh 2.5 times what you weigh on Earth. If you weigh 70 kilograms on Earth, you would weigh 175 kilograms on Jupiter. Every step would require 2.5 times the energy. Your skeleton would be bearing 2.5 times the load. Your heart would be pumping blood against 2.5 times the gravitational resistance. The 2019 physics teacher study on exoplanetary gravity concluded that humans could theoretically walk at up to about 4 times Earth's gravity with rigorous training. Jupiter's 2.5 G is within that range, but barely. It would be exhausting. It would probably cause long-term damage to joints, cardiovascular systems, and bones. A 2008 study in the Journal of Experimental Biology examined how gravity affects walking using predictive models based on inverted pendulum mechanics. The study found that the relationship between stride length and walking speed changes significantly with gravity. At higher gravity, optimal walking speed decreases. You would walk more slowly, take shorter steps, and expend more energy doing so. Our assumption of 5 kilometers per hour becomes questionable on Jupiter, but let us maintain it for the sake of comparison. 30 years to walk around Jupiter. And of course, you cannot actually walk on Jupiter. There is no surface, just atmosphere getting progressively denser as you descend, eventually transitioning into a strange state of matter that is neither liquid nor gas. At some point deep inside, there might be a core of rock and ice, but you would be crushed by pressure long before you reached it. Still, 30 years. To put that in perspective, in 1977, NASA launched the Voyager 1 and Voyager 2 spacecraft. Voyager 1 passed Jupiter in March 1979 and has been traveling outward ever since. As of 2025, Voyager 1 is still operating, still sending data back to Earth, and has now been in space for nearly 48 years. Our hypothetical walk around Jupiter would take about 2/3 as long, as Voyager 1 has been traveling through space. The Galileo spacecraft, which arrived at Jupiter in 1995, spent 8 years studying the planet and its moons before being deliberately plunged into Jupiter's atmosphere in 2003. Our walk would last nearly 4 times longer than that entire mission. And what would you see during those 30 years? The bands of Jupiter, the alternating light zones and dark belts that circle the planet, are made of clouds at different altitudes. The light zones are higher, made of ammonia ice crystals. The dark belts are lower and contain ammonium hydrosulfide and other compounds. The boundary between them generates ferocious storms. The Great Red Spot, the most famous storm in the solar system, is a high-pressure anticyclone that has been observed for at least 350 years. It is currently about 16,000 kilometers wide, larger than Earth. During your 30-year walk, you would circle the planet about 3 times. Jupiter rotates every 10 hours, so the storm would pass beneath you roughly every 10 hours as well. You would see the Great Red Spot thousands of times, watching it from different angles at different lighting conditions. Recent observations from the Juno spacecraft, which has been orbiting Jupiter since 2016, have revealed that the Great Red Spot extends at least 300 kilometers deep into Jupiter's atmosphere, and possibly much deeper. It is not just a surface phenomenon. It is a 3-dimensional structure that penetrates far into the planet. The lightning on Jupiter is unlike anything on Earth. Jovian lightning occurs predominantly near the poles and in the deep atmosphere, where water clouds exist. Individual flashes have been detected that are hundreds of times more energetic than the most powerful lightning on Earth. During your 30-year walk, you would see these flashes illuminating the clouds above and below you, brief moments of brilliant light in the roiling atmosphere. Jupiter's magnetic field is the strongest of any planet, about 20,000 times stronger than Earth's. It traps charged particles from the solar wind, creating intense radiation belts around the planet. Walking on Jupiter, if you somehow survive the gravity and pressure and lack of solid ground, the radiation would still kill you. The inner radiation environment around Jupiter is one of the most hostile in the solar system. But we said we would ignore the lethal aspects. 30 years of walking through the bands and storms of Jupiter, watching the 4 Galilean moons dance through the sky, seeing the sun shrink to a small bright point no larger than Venus appears from Earth. Saturn comes next, the ringed wonder. Saturn's equatorial diameter is 120,536 kilometers, making it the second largest planet. Its circumference is approximately 378,675 kilometers. At 40 kilometers per day, that is 9,467 days of walking, 25.9 years. Almost as long as Jupiter, but not quite. Saturn is smaller, even though its rings make it look impossibly huge in photographs. The gravity on Saturn, measured at the 1-bar pressure level, is 10.4 meters per second squared. That is almost exactly the same as Earth's gravity. Walking on Saturn would feel almost normal, at least in terms of the gravitational pull on your body. This is counterintuitive. Saturn is enormous. It masses 95 times as much as Earth, but it is also incredibly diffuse, with an average density lower than water. If you could find an ocean large enough, Saturn would float. Its enormous mass is spread over such a huge volume that the gravitational pull at its surface is surprisingly gentle. 26 years to walk around Saturn, almost exactly the length of a single Saturnian year, which lasts 29.4 Earth years. You would experience most of a complete cycle of Saturnian seasons during your walk. And what a walk it would be. Saturn's atmosphere features bands of clouds and massive storm systems, including a bizarre hexagonal storm at its north pole that has persisted for decades. The wind speeds in Saturn's upper atmosphere exceed 1,800 kilometers per hour in some regions. You would walk through an atmosphere of hydrogen and helium, surrounded by ammonia ice crystals, with those famous rings arcing across the sky. From Saturn's equator, the rings would appear as a thin, bright line bisecting the heavens, because you would be looking at them edge-on. 26 years, an entire adult career. You could be hired out of college to walk around Saturn and retire when you finished. The rings would dominate your experience on Saturn in a way that nothing dominates any experience on Earth. From Saturn's equator, you would be inside the ring plane. The rings would appear as a bright band stretching from horizon to horizon, bisecting the sky. At certain times, with the sun on the other side of the rings, they would appear as a dark line against the backdrop of space. At other times, lit from your side, they would glow brilliant white. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, revealed that the rings are far more complex than early astronomers imagined. They are not solid surfaces, but collections of countless particles, ranging from dust grains to chunks the size of houses. These particles orbit Saturn at different speeds depending on their distance from the planet, creating a dynamic, churning system. During your 26-year walk, the rings would not appear static. You would see structure within them, waves and ripples caused by the gravitational influence of Saturn's 146 known moons. You would see the gaps, like the Cassini division, where resonances with moons have swept the area relatively clear of debris. And you would see the moons themselves. Titan, the largest, would be visible as a small orange disk, its thick atmosphere giving it a distinct color. Enceladus, which Cassini discovered, is geologically active, with geysers of water ice erupting from its south pole, would appear as a bright point of light. The Sun from Saturn is only about 1% as bright as it is from Earth. The illumination on Saturn would be similar to twilight on our planet, bright enough to see, but dim enough that stars would be visible even during the day. You would walk through a permanent dusk, the rings glowing overhead, the moons tracking across the sky in their complex orbital dances. Saturn's atmosphere, like Jupiter's, features bands and storms, though they are generally more subdued. The hexagonal storm at Saturn's North Pole, discovered by Voyager and studied extensively by Cassini, is one of the most mysterious structures in the solar system. Each side of the hexagon is longer than Earth's diameter. No one fully understands why it maintains its shape. 26 years in that eerie twilight, surrounded by rings, walking on clouds that are not solid, under gravity that feels almost like home. We reach the ice giants now, the distant worlds that no spacecraft has visited since the Voyager flybys of the 1980s. Uranus has an equatorial diameter of 50 to 1,118 kilometers. Its circumference is approximately 160,592 kilometers. At 40 kilometers per day, walking around Uranus would take 4,015 days, exactly 11 years. The gravity on Uranus is 8.87 meters per second squared, slightly less than Earth's. You would feel about 10% lighter. Walking would be comfortable, perhaps even pleasant in gravitational terms. But Uranus is strange in other ways. It rotates on its side with an axial tilt of nearly 98 degrees. This means its seasons are extreme in a way no other planet experiences. During the Uranian summer, One pole points almost directly at the sun, while the other is in continuous darkness. The equator, where we are walking, experiences a bizarre cycle of lighting as the planet rolls around its 84-year orbit. Speaking of which, a year on Uranus lasts 84 Earth years. During our 11-year walk, we would experience only about 13% of a Uranian year. The seasons would not change dramatically during our journey. Uranus is cold. Its effective temperature is around -224 degrees Celsius. It is the coldest planet in the solar system, colder even than Neptune, despite being closer to the Sun. The reason is not fully understood, but it may have something to do with Uranus's lack of internal heat generation compared to other giant planets. 11 years in the blue-green murk of Uranus's atmosphere. 11 years of cold, distant sunlight and wind speeds reaching 900 kilometers per hour. Uranus is the forgotten planet. Between Voyager 2's flyby in January 1986 and the present day, no spacecraft has visited it. Everything we know about Uranus comes from that single encounter nearly 4 decades ago, supplemented by Earth-based and Hubble Space Telescope observations. Voyager 2 found a world that defied expectations. Uranus's extreme axial tilt means its magnetic field is tilted 59 degrees from its rotational axis and offset from the planet's center by about 1/3 of its radius. The magnetic field tumbles through space in a way unlike any other planet. The atmosphere itself appears bland at first glance, a nearly featureless blue-green sphere. The color comes from methane in the upper atmosphere, which absorbs red light. But beneath that serene exterior, scientists now know there is activity. Infrared observations have revealed clouds and storm systems that were invisible to Voyager's cameras. Walking on Uranus, you would exist in a world of profound strangeness. Because of the axial tilt, the sun's path through the sky would be unlike anything you have ever experienced. For part of the Uranian year, the sun would spiral around the sky, never setting, but never rising to a fixed noon position either. For another part, it would remain below the horizon for decades at a time. During our 11-year walk, the lighting would change continuously but slowly. The seasons on Uranus last 21 Earth years each. We would experience roughly half a season during our journey, the lighting gradually shifting, the shadows slowly changing angle, and the cold. Uranus is cold in a way that is difficult to comprehend. At -224 degrees Celsius, it is colder than Neptune, colder than any other planet, despite being closer to the Sun. The reason may be that Uranus, unlike the other giant planets, has no significant internal heat source. Whatever primordial heat it once had has dissipated into space, leaving a world that is barely warmer than absolute thermodynamic zero. 11 years, long enough for a child to be born and enter 6th grade, long enough for governments to rise and fall, long enough for technologies to become obsolete. Neptune, the final planet, the edge of the classical solar system. Neptune has an equatorial diameter of 49,528 kilometers. Its circumference is approximately 155,600 kilometers. At 40 kilometers per day, that is 3,890 days of walking. 10.7 years, slightly smaller than Uranus, slightly less time to walk around. The gravity on Neptune is 11.15 meters per second squared, about 14% stronger than Earth's. You would feel noticeably heavier, but not oppressively so. It is comparable to Jupiter's moons, where future astronauts might one day walk. Neptune is the windiest planet in the solar system. Wind speeds in its upper atmosphere have been measured at over 2,100 kilometers per hour. These winds blow in the opposite direction from the planet's rotation, a phenomenon called retrograde motion that is still not fully understood. The Great Dark Spot, observed by Voyager 2 in 1989, was a storm system nearly the size of Earth. It has since disappeared, but other dark spots have formed. Neptune's atmosphere is dynamic, active, constantly churning. A year on Neptune lasts 164.8 Earth years. During our nearly 11-year walk, we would experience only about 6.5% of a Neptunian year. The planet would barely notice our passage. 10 years and 8 months to walk around Neptune. And then we are done. Neptune would be the most dynamic of the giant planets to walk on. If you could walk on it, despite being the most distant planet, receiving only 1/900th the sunlight that Earth receives, Neptune has the most violent weather in the solar system. The winds come from Neptune's internal heat. Unlike Uranus, Neptune generates about 2.6 times as much energy as it receives from the Sun. This internal warmth drives convection in the atmosphere, creating winds that exceed 2,000 kilometers per hour. For comparison, the fastest tornado ever recorded on Earth had winds of about 500 kilometers per hour. Walking on Neptune would mean walking through a hurricane that never ends, that spans an entire planet, that has been blowing for billions of years. Voyager 2, which flew past Neptune in August 1989, photographed the Great Dark Spot, a storm system the size of Earth. By the time the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had vanished. But other dark spots have appeared since. Neptune's atmosphere is constantly churning, constantly regenerating these massive storm systems. The color of Neptune is a more vivid blue than Uranus, despite having a similar composition. Scientists believe this is because there is additional, as yet unidentified compound in Neptune's atmosphere that absorbs red light more efficiently. From Neptune, the Sun would be barely distinguishable from a bright star. It would still be the brightest object in the sky, but it would not provide warmth. It would not provide significant light for photography. You would walk in eternal near darkness, with only starlight and the faint glow of Neptune's aurora for illumination. Neptune has 16 known moons, the largest of which is Triton. Triton is remarkable because it orbits Neptune in the opposite direction from the planet's rotation, a retrograde orbit that indicates it was captured from the Kuiper belt rather than forming with Neptune. Triton has active geysers that erupt nitrogen gas and dust particles into space, making it one of the few geologically active worlds in the outer solar system. From Neptune's cloud tops, Triton would appear as a small pink disk, larger than any moon appears from Earth, moving backwards across the sky as it follows its retrograde orbit. 10 years and 8 months, the most distant leg of our journey, the edge of the planetary solar system. Let us add it all up. Mercury, 383 days. Venus, 951 days. Earth, 12 days. Mars, 534 days. Jupiter, 11,230 days. Saturn, 9,467 days. Uranus, 4,015 days. Neptune, 3,890 days. Total, 30 to 1,472 days. That is 86.2 years. 86 years of walking, a full human lifetime. If you started walking on the day you were born, walking around every planet in the solar system would take you past your 86th birthday. The average life expectancy in developed countries is now approaching 80 years. To complete this journey, you would have to walk for longer than most people live. And this is with our generous assumptions. 8 hours of walking per day, every day, with no breaks, injuries, illnesses, or interruptions. In reality, any attempt to actually walk for 86 years would require rest periods, recovery time, and probably medical intervention. Consider the logistics for a moment. Over 86 years, you would need approximately 31,500 meals. At even a modest 2,000 calories per day, that is 63 billion calories of food, you would need thousands of pairs of shoes. You would need shelter every night for over 31,000 nights. You would need medical care, dental care, psychological support for the profound isolation of walking alone through alien landscapes for decades. None of this is possible, of course. Even on Earth, the longest continuous walks have required extensive support teams, supply drops, and periods of rest. Walking for 86 years straight is beyond the capacity of any human being who has ever lived. But the number itself tells a story. Here is what strikes me about this calculation. Most of those 86 years are spent on just 2 planets. Jupiter and Saturn alone account for 20,697 days. That is 56.7 years. Nearly 66% of the total journey. The 4 rocky planets, including Earth, take only 2,870 days combined, less than 8 years, about 9% of the total. This is a physical representation of something astronomers try to explain with numbers and diagrams. The gas giants are not just big, they are incomprehensibly big. They dominate the solar system in a way that photographs cannot convey. When you see an image of Jupiter next to Earth, you can intellectually understand that Jupiter is larger. You can read that Jupiter's diameter is 11 times Earth's. But knowing something and feeling something are different. Walking makes you feel it. 30 years around Jupiter, 26 around Saturn, a year and a half around Mars. The disparity is visceral. Consider what you would experience in those 30 years on Jupiter. You would watch 30 years of human history unfold on the radio news from Earth, delayed by 40 minutes or so each way. Whole generations would be born, grow up, and start their own lives while you were still walking. Technologies would change. Countries would change. People you knew when you started would die of old age before you finished, and you would still be walking, step after step, through the ammonia clouds, beneath the lightning storms, past the great red spot for the 1,000th time. That is what scale means. Not numbers in a textbook, not statistics about diameters and distances. Scale means time. Scale means the accumulation of moments beyond counting, the accretion of experiences beyond comprehension. And this is just the planets. We have not discussed the distances between them. If you were to walk from Earth to Mars at 5 kilometers per hour, covering 40 kilometers per day, how long would that take? At Mars's closest approach to Earth, the distance is about 55 million kilometers. At 40 kilometers per day, that would take 1,375,000 days to walk. That is 3,767 years. Nearly 4,000 years just to walk from Earth to Mars. The entire span of recorded human history. The pyramids of Egypt were built about 4,500 years ago. If the ancient Egyptians had started walking to Mars the day they laid the first stone, they still would not have arrived. And that is when Mars is closest. At its farthest, Mars can be over 400 million kilometers from Earth. Walking that distance would take more than 27,000 years. Let that number settle. 27,000 years. That is longer than the time since the last ice age ended. It is longer than the history of civilization. If Neanderthals had started walking to Mars when they were still the dominant hominid in Europe, they would just now be approaching their destination. And Mars is our nearest neighbor among the outer planets. Jupiter is 11 times farther at its closest approach. Saturn is 17 times farther. Neptune is 60 times farther. To walk to Neptune would take well over 200,000 years. That is longer than anatomically modern humans have existed. The solar system is not just big, it is empty. The planets are specks in a void so vast that walking across it would consume geological ages. This emptiness is one of the most difficult things for the human mind to grasp. When we see diagrams of the solar system, the planets are typically shown close together so they all fit on the page. This creates a fundamentally false impression. In reality, if you drew the planets to scale, with the Sun the size of a basketball, Earth would be a small bead about 26 meters away. Jupiter would be a golf ball about 134 meters away. Neptune would be a marble about 780 meters away. The space between planets is not just large, it is vast beyond comprehension. The void between worlds is so immense that light, the fastest thing in the universe, takes hours to cross it. A spacecraft traveling at tens of thousands of kilometers per hour takes years to reach the outer planets. And we are talking about walking at 5 kilometers per hour. Walking the speed at which our ancestors crossed continents over thousands of years. Walking the pace that evolution designed us for. The mismatch between human walking speed and interplanetary distance is so extreme that it borders on the absurd. It is like measuring the distance to a star in millimeters, or the age of the universe in heartbeats. The units do not fit. They were not meant to fit. But there is something illuminating about forcing them to fit anyway, about translating cosmic distance into human terms, even when those terms become meaningless numbers. 4,000 years to walk to Mars. That number is absurd. It is impossible. But it tells you something that the number 55 million kilometers does not. It tells you that Mars is not just far, it is unreachably far by human locomotion. It is separated from us by spans of time that exceed the entire history of civilization. And Mars is close. Johannes Kepler, the German astronomer who discovered the laws of planetary motion in the early 17th century, spent years trying to understand why the planets move the way they do. His third law, published in 1619 in his work Harmonices Mundi, states that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. Kepler did not know about gravity. Isaac Newton would not publish the Principia with its theory of universal gravitation until 1687, nearly 70 years later. Kepler just knew that there was a mathematical relationship, a harmony in the heavens that his calculations revealed. In his notebook, upon discovering the third law, Kepler wrote words that still resonate 4 centuries later. I first believed I was dreaming, but it is absolutely certain and exact that the ratio which exists between the periodic times of any two planets is precisely the ratio of the 3/2 power of the mean distances. He had spent decades working with the observational data of Tycho Brahe, the Danish astronomer whose meticulous measurements of planetary positions were the most accurate the world had ever seen. Kepler inherited Brahe's data when the older astronomer died in 1601, and he spent the rest of his life trying to make sense of it. The first 2 laws, describing the elliptical shapes of planetary orbits and the way planets speed up and slow down as they move closer to and farther from the Sun, were published in 1609. But it was the third law that had the most profound implications. It connected the orbital period of a planet, the time it takes to complete one journey around the Sun, to its distance from the Sun. What Kepler discovered, and what our walking experiment illuminates, is that the solar system has structure. It is not random. The planets are spaced according to physical laws that govern their orbits, their sizes, their distances, their orbital periods, all follow from the interplay of mass and gravity. Newton would later prove that Kepler's third law was a direct consequence of the inverse square law of gravity. But Kepler found it first, empirically, through sheer mathematical persistence. When we walk around each planet, we are tracing that structure with our feet. We are measuring, in the most primal way possible, the geometry of our cosmic neighborhood. 86 years to walk around every planet, 4,000 years to walk to Mars, 200,000 years to walk to Neptune. These numbers are incomprehensible in practical terms. No human will ever walk around Jupiter. No human will ever walk to Neptune. But thinking about it changes something. The Apollo astronauts who walked on the moon covered only a few kilometers during their excursions. The entire distance traversed by all 12 moonwalkers combined is less than 100 kilometers, less than a single day of our hypothetical journey. Yet those few steps changed humanity. They proved that walking on another world was possible. They established that the vast distances of space could be crossed, at least for the short hop to our nearest neighbor. The experience of walking in lower gravity was stranger than most of the astronauts expected. Neil Armstrong noted in his debrief that balance while walking was not difficult, but he nearly fell over backwards when attempting a high jump. Buzz Aldrin experimented with different gaits and found that a standard 1 foot in front of the other walk worked better than the kangaroo hop many had predicted. Charlie Duke, on Apollo 16, attempted to set a lunar high jump record. He pushed off as hard as he could and immediately tipped over backwards, landing on his portable life support system backpack. In his memoir, he admitted that for a terrifying moment, as he fell in slow motion, he was certain he was about to die. Fortunately, neither his suit nor his backpack was damaged. The Apollo moonwalks lasted only a few hours each. The longest single EVA was just over 7 hours. By the later missions, Apollo 15, 16, and 17, the astronauts had lunar rovers that allowed them to drive across the surface rather than walk. Even so, they found that walking for extended periods in the bulky spacesuits was exhausting. Heart rates during the moonwalks regularly exceeded 130 beats per minute and occasionally spiked much higher during strenuous activities. Walking on the moon, the Apollo astronauts discovered, was both easier and harder than expected. Easier because the lower gravity meant less work with each step. Harder because the suits were cumbersome, the terrain was deceptive, and there was no atmosphere to dissipate heat from their bodies. The moon's equatorial circumference is 10,921 kilometers. At 40 kilometers per day, it would take 273 days to walk around it. Less than Mercury, manageable, almost. In human terms, future astronauts may walk significantly farther on the moon. The Artemis program aims to establish a sustainable human presence there. Walking on the moon may become, if not routine, then at least something humans do. Mars is the next target. The Martian circumference of 21,340 is not that much larger than the great walking journeys already accomplished on Earth. A year and a half of dedicated walking in a lower gravity environment that might actually be easier on the body than Earth. It is not impossible to imagine a future where someone walks around Mars. There is something profound about that possibility. For all of human history, Mars has been a point of light in the sky, a mystery, a canvas for our imagination. Giovanni Schiaparelli saw canals on Mars in 1877. Percival Lowell built an entire observatory to study what he believed was a dying civilization clinging to those canals, building them to carry water from the poles to the equatorial cities. The canals were optical illusions. The civilization was fantasy, but the desire to walk on Mars, to know it intimately, to trace its contours with human feet, that desire is real. It has been real since we first looked up and noticed that Mars moves differently than the stars. In the 21st century, we have sent robots to walk on Mars for us. The Spirit and Opportunity rovers, active from 2004 to 2010 and 2018 respectively, drove across the Martian surface for years. Curiosity has been driving since 2012 and Perseverance since 2021. The Chinese Zhurong rover explored Mars from 2021 to 2200. These robots have collectively driven hundreds of kilometers across Mars. Opportunity alone traveled more than 45 kilometers in its 15 years of operation. That is more than a single day's walk in our thought experiment, more than all the Apollo astronauts ever covered on the moon, but still a tiny fraction of the 21,344 kilometers around Mars's equator. Someday, humans will walk where those robots drove. Someday, human footprints will mark the red dust, and human eyes will see the salmon-pink sky. When that happens, everything we have calculated here will become more than a thought experiment. It will become a challenge, a dare, a question that begs to be answered. Can we walk around this world? But Jupiter, Saturn, the ice giants, these remain in the realm of the imagination, not just because we cannot land on them, but because of what they represent. They represent scale that exceeds human comprehension. They are worlds so large that walking around them would consume an entire life. This is what our thought experiment ultimately reveals. The solar system is sized beyond human scale. We can visit it. We can photograph it. We can send robots to study it. But we cannot walk it. Not really. Not in the way we walk the Earth. Walking is intimate. It connects you to terrain in a way that flying or driving cannot match. Every step is a negotiation with the ground, a conversation between your body and the world beneath your feet. To walk around a planet is to know it in the most fundamental way. We know Earth this way. We could know the Moon this way. We could know Mars this way. But Jupiter and Saturn and Uranus and Neptune, we will know only at a distance. We will see them through telescopes and spacecraft. We will model them with computers and study them with instruments, but we will never walk them. And maybe that is okay. Maybe that is what makes them sublime. The word sublime, in its original philosophical sense, refers to something that exceeds our capacity to comprehend, something that is both terrifying and beautiful, precisely because it is too big for us. The philosopher Edmund Burke, writing in the 18th century, defined the sublime as that which causes the strongest emotion the mind is capable of feeling. The sublime is vast, powerful, and ultimately beyond human control. It induces a kind of delightful horror, a mixture of fear and admiration. Jupiter is sublime. Saturn is sublime. The whole solar system, in its vast and intricate architecture, is sublime. 86 years to walk around every planet. A human lifetime spent in motion, one step at a time, circling worlds. It will never happen. It cannot happen. But thinking about it, calculating it, imagining it, reveals something true about where we are. We are small. The universe is large, and the distance between those two facts is measured in footsteps that will never be taken. There is a famous passage in the Tao Te Ching. A journey of 1,000 miles begins with a single step. Our journey of 31,472 days of 86.2 years would require approximately 2.3 billion steps, assuming an average step length of about 0.7 meters. 2.3 billion steps around 8 worlds. Every single one of those steps would be a small act, lasting perhaps half a second, but accumulated, repeated, sustained across decades, they would trace the geometry of the solar system. That is perhaps the deepest lesson of this thought experiment. Grand things are made of small moments. Vast distances are crossed one unit at a time. The incomprehensible scale of the cosmos is built from comprehensible pieces. Every number in this exercise, no matter how astronomical, reduces ultimately to the same simple act, putting one foot in front of the other. And that act, repeated beyond counting, can trace the circumference of worlds. You cannot walk to Jupiter, but you can take a step. You cannot circle Saturn, but you can put one foot in front of the other. And maybe that is how we should think about our place in the universe. Not as beings who will one day stride across the stars, but as beings who can take small steps, accumulate them, and see how far we get. Our ancestors walked out of Africa perhaps 70,000 years ago. They walked across continents, over ice bridges, through deserts and forests and mountains. They walked to every corner of this planet, carried by nothing more than their legs and their determination. We are the descendants of walkers. Walking is in our blood, in our bones, in the very structure of our spines and hips and feet. We evolved to walk. It is what we do. And now we dream of walking on other worlds. We send our machines first, our scouts, our robotic eyes and wheels. But behind them, always, is the dream of human footprints, the dream of the walk. 86 years of walking, a lifetime of steps. That is how long it would take to orbit every planet in our solar system. The numbers are impossible. The journey is impossible. But the dream of it, the imagining of it, tells us something about ourselves. We are creatures who measure the cosmos in footsteps. We are creatures who look at the vastness of space and ask, how long would it take to walk there? That impulse, that instinct to translate the infinite into the human, to make the inconceivable comprehensible, that is what makes us who we are. So consider, the next time you take a walk, consider what you are doing. You are performing the same action that could, in theory, carry you around Mercury in a year, around Mars in 18 months, around Jupiter in 3 decades. Every step you take is a small echo of the impossible journey we have calculated here. Every footfall is a tiny fraction of 2.3 billion steps. Every walk you take, whether to the store or around the neighborhood or along a mountain trail, connects you to the vast distances we have imagined. The solar system is vast beyond measure, but you are walking through it right now on this small blue planet that orbits the sun. You are part of the cosmic dance, moving through space at 30 kilometers per second as Earth circles its star, walking on a world that is itself walking around the sun. And that is not nothing.